Welcome to the third of our three lectures on multi-level explanation. The first lecture was about classical reductionism and some of the standard criticisms of it. The second lecture was about the anti-reductionist consensus that formed in response to those criticisms and looked at some forms of pluralism in the philosophy of science. In this final lecture, we're going to consider the ontological turn and the re-emergence of emergence. So the ontological turn is a turn away from thinking about the issues around multi-level explanation and reduction in terms of explanatory relationships between theories, and instead to focus on reduction as an account of the ontological relationships between the subject matter of scientific theories, so the things, the stuff that it's talking about. So here's the structure of the lecture. First of all, talk about the ontological turn, and we'll dig a bit deeper into the structure of Jae-Kwon Kim's causal exclusion argument. We'll then have a quick look at the re-emergence of emergence, where the term has come from in the history of philosophy and of science. And then we'll look at how to define emergence, how to understand it as a claim. What is it claiming? Then we'll look at across some examples from the natural sciences, and then we'll dig down into one of those examples. This is Tom McLeish's account of emergence in soft matter physics. We'll finish up by very briefly considering an issue which has been in the background of the reductionist position, which is the completeness of physics, and it continues to be an issue of disagreement between the temperamental reductionists on the one hand and temperamental anti-reductionists on the other. As I said, the ontological turn involves a turn towards metaphysical issues in the relationship between the special sciences, including the study of mental properties and events in psychology, and fundamental physics. Kim challenges non-reductive physicalism, which, as we saw, was a central feature of the anti-reductionist consensus, with a question. According to non-reductive physicalism, are mental properties causally efficacious? In other words, do they change things in the physical world, or are they epiphenomenal? That is, they're there, we can see them, but maybe they don't really make a difference. Now, intuition tells us that mental properties can't be epiphenomenal, they must be causally efficacious. So, to use an example I discussed in the last lecture, I decide to go to the library, and that's a mental event, and then sometime later my body is actually walking towards the library. So if my decision, which is a mental event, caused a physical event, namely my walking towards a library, then it must be possible for mental events somehow to intervene in the course of physical events. But how is that supposed to work, says Kim, on the non-reductive physicalism picture? And he crystallizes the objection around the following sharply stated argument. This kind of argument, the problem of causal exclusion, has been central to discussions of mental causation, that is, the idea that the mind or mental events can bring about things, changes in the physical world, for the last 20 years. So the argument basically consists of three premises, 1, 2, 3, and a conclusion, which we've labelled 4. So the first assumption is that mental and physical events are distinct. This is a central assumption of non-reductive physicalism. If you're a non-reductionist about mental events, then you must say that they are distinct from physical events. The second assumption, and this is a controversial one as we shall see, is that every physical event has a complete physical cause. Now, a quick way to defend this sort of assumption is that is to say that there's nothing spooky going on in the world. So the kinds of changes that happen in the world are physical changes. So we have transfers of energy or charge or mass from one place to another, and that's what causation consists in. So a physical process would be, for instance, the sun emitting light, which travels towards the world, to the Earth, taking, I believe, about 8 minutes or so. That's a process. But there's a transfer of something there, the energy embodied in the light. So if those are the only kinds of processes that are happening in the world, then surely every physical event must have a complete physical cause, because you just have to look at those kinds of processes to find the physical causes of an event. And if there's nothing additional spooky intervening, there we go. Every physical event has a complete physical cause. A third, less obvious assumption is that there's no causal overdetermination. So if there's no causal overdetermination, then that rules out every physical event having a complete physical cause and also another kind of non-physical cause, for instance. So causal overdetermination, I mean, imagine that there are two groups of assassins who are trying to kill someone, and they both kill the victim at exactly the same time. Well, which of them is the cause? You know, it seems like there's a coincidence that they managed to bring about the death of the victim at exactly the same time. And it might be hard to assign causal responsibility there, but we'd like to say that one of them must have got there first, unless there's a super kind of coincidence going on. So those are the three premises of the argument, and if those three premises are true, then it seems we must accept the conclusion that mental events cannot be the causes of physical events, because mental events are distinct from physical events, so they can't occur in the list of complete physical causes appearing in line 2. There's no causal overdetermination, so there's no space for them to intervene in a kind of a spooky way or an additional way over and above the complete physical cause. So basically the complete physical cause crowds out any other kind of influence. Therefore, mental events cannot be the causes of physical events. So, if we want to avoid the conclusion, which of course is an unattractive one, if we think that, for instance, my decision to go to the library can be part of what brings about my body actually starting to walk towards the library, then we've got to be able to challenge one of the assumptions or the structure of the argument, but we're not going to consider that here. Kim's own response to the problem of mental causation is to argue that the causal efficacy of mental events and properties demands that mental events and properties are reducible to physical events and properties. Now, there's a couple of things to note here, importantly, about the problem of mental causation. One is that it generalizes. So there's nothing specific about the, as it were, the philosophy of mind setting. The causal efficacy problem generalizes and applies to any special science events and properties unless it's already priced in that those special science events and properties are in some sense physical, in which case the problem doesn't arise because they're already counted among the physical. That would be one way, for instance, to think about the relationship between chemistry and physics. It's just part of the physical. The second thing to note is that Kim's argument relies on this very strong claim about the completeness of physics. So one obvious place for anti-reductionists to try to avoid Kim's problem is by challenging the completeness assumption. An alternative is overdetermination, but as it were, it's less of the attractiveness is less obvious. I now turn to emergence. Now, the connection between emergence and Kim's causal exclusion problem may not immediately be obvious, but I'll bring it about in a moment. I'm going to introduce the topic by taking you through the history of emergence. The term goes back to the 19th century. It is, etymologically speaking, it's the term is grounded in one thing coming out of the other. Like as if, when someone's swimming, they can emerge from the sea. Well, if you've got the physical, then, as it were, other non-physical things might be able to emerge out of the physical. They're kind of hidden there or latent, and then they get brought out. Its key point in philosophy has always been to be a middle way between a reductionist position, which is according to which basically everything is material or physical, and a view according to which the special science, whatever it is entirely ontologically independent of the physical. So it's not grounded in the physical at all. So if you imagine here's the extreme ontological independence position, here's the reductionist position. Well, emergentism is sort of in the middle, combining a kind of dependence that reduction sees and the independence that radical ontological independence sees. So the idea, but not the term, of emergence was used by John Stuart Mill when he made a distinction between heteropathic and homopathic laws. So Mill's idea was that physical sciences combine causes, and it gives you ways to combine causes. And everything you can combine, given the ways that the physical sciences tell you about how to combine causes in a sort of a natural way you can assemble, that's homopathic. So any law you can explain by an ordinary kind of physical composition of causes would be a homopathic law, according to Mill. He contrasted that homopathic laws with heteropathic laws, so that heteropathic laws are laws that you can't explain. So, but these heteropathic and homopathic laws are both kinds of laws which govern the behaviours of physical material stuff. So Mill's thought is that there are some ways that physical stuff behaves that is in some sense accessible to the reductionist, and there are some ways that are not so possible to be understood. That's the heteropathic behaviour. The term evolution is introduced by Conway Lloyd Morgan in his book Emergent Evolution. And Lloyd Morgan's idea is that evolutionary development, so he was writing in the late 19th century and early 20th century, evolution, Darwinian evolution, builds structure upon structure, and it's this kind of ability that provides the possibility for emergence. So a structure would evolve at one stage, and then that enables the evolution, the development of further structures which presuppose the existing structures. And it's that kind of historical development which is characteristic of some models of emergence. And Lloyd Morgan's other idea is that evolution needn't be a process that happens at the same pace all the time, but it might happen very quickly sometimes when you get a qualitatively new kind of structure coming out of the built upon structures which have previously evolved. So mentality would be a prime example of that, or life. As you see, these are the central emergentist ideas. Another British emergentist is Samuel Alexander, who it gives us, to modern philosophy, Alexander's dictum, which is the idea that if we want to see one thing, a high-level thing, as it were, distinct from a lower-level thing, then we have to see it as having additional causal powers. This is a very familiar idea in philosophy, going back to Plato, who in the Sophist has the Eleatic stranger saying, well, if something's got going to be added to our ontology, like the list of things that we think of as existing, then it has to have an explanatory role to play. It has to be doing something. So there's kind of a requirement of causal efficacy before we think of something as existing. And in the context of reduction and emergence, if we want to see something existing over and above something else, then we've got to think of it as having additional causal powers over the thing that is emerged from. That's a central idea in British emergentism. And then finally, we get on to C.D. Broad, who I've written about quite a bit myself, who was the last in the series of British emergentists, who made a distinction between resultant and configurational forces that very much parallels Mill's distinction between heteropathic and homopathic laws. So the resultant forces are those that can be assembled from fundamental physical forces. But, says Broad, resultant forces are not enough to explain everything that happens in the world. We sometimes have to appeal to these configurational forces, which just arise in particular arrangements of things, and these configurational forces ground additional causal powers. Broad didn't quite put it like that. That would be my rephrase or reapplication of the idea of additional causal powers. But anyway, the point is that the reductionist sees the world as being assembled in a certain way, but Broad and the other emergentists don't think that that's a sufficiently rich account of what's going on in the world. Now, there's a couple of excellent summaries of British emergentism. The term British emergentism goes back to the philosopher Brian McLaughlin, who wrote a really marvellous long article in 1992 about this, which you'll see in the references. So that's one aspect of the history of emergence. That's really where the term emergence comes, as we understand it, comes to have its current meaning of something being assembled out of something else, and being in some sense autonomous or new with respect to whatever it's assembled out of. Now, the other key and quite distinct tradition, although it's related historically, is the use of emergentist ideas in biology and systems theory between the 1920s and the 1950s, and in fact all the way down to the current time. And once again, it's used in two contexts really. One is to give a sort of middle way between vitalism, so the thought that life is something that's kind of superadded to matter in order to create living things. So that vitalism is one of these views according to which life is, as it were, ontologically quite independent of matter. That's vitalism. On the other hand, there's reductionism, which is that life is reducible to straightforward matter. And then somewhere in between is the view that life is an emergent property of some physical system. So we have the dependence of reductionism and the independence of vitalism. The other place that emergentist ideas have contributed within biology is in thinking about biological systems as complex systems, and the way that they build upon existing structures and are themselves structured by evolution. Biological systems as complex systems. From the 1970s, after a very influential paper, short paper by Philip Anderson entitled More is Different. That's Anderson's 1971 paper. Emergentist ideas came pretty explicitly up within condensed matter physics. Now, condensed matter physics grew out of a discipline called solid state physics, which historically, and it's always had an independence problem. So condensed matter physics deals with things going on at the kinds of temperatures we see around us, very much similar temperatures to temperatures and energy ranges considered as are considered by chemistry. But it looks in a different way, as a kind of the way physics looks at them. Anderson considers emergence as a good way to describe symmetry breaking in physics. The important mathematical point, which is distinct to the way that emergentist ideas are expressed in condensed matter physics, is that symmetry breaking, well, explaining symmetry breaking depends on important explanatory assumptions which have no non-circular derivation from more basic physical laws. So there, in some sense, there's this kind of explanatory autonomy. And Anderson's ideas have been taken up by many other physicists, and there really is a strong tradition of emergentist thinking in condensed matter physics, and we'll see a little bit more of it later on. Now, emergentist ideas within philosophy were quite unfashionable for a number of years after C.D. Broad. C.D. Broad's major work, The Mind and Its Place in Nature, was published in 1925, and it probably logical positivist critiques which made emergentism seem unfashionable. Some of the logical positivists, including Ernest Nagel, who we've seen from and who discusses emergentism quite dismissively in his book The Structure of Science, which we mentioned in one of the in the first lecture. Nagel says that really the difference between emergentism and other positions is just a kind of a form of words. Emergentism seems to be using an informative metaphysical vocabulary, but in fact it's just a way of redescribing the phenomena that he was talking about, which were the relationships between theories. I think nobody thinks that Nagel was right about that these days. And what has happened is that emergence has re-emerged as a plausible and widely accepted position from the late 1990s as a response to the kinds of problems that Kim gave us about the possible causal exclusion of the special sciences. So in some sense, either the causal efficacy of the special sciences drains down to the lowest level by they can only affect anything, the way the course of events in the world, through their being realized by and identical with physical events. So they have no distinct power. So emergentism gives a way to challenge that. But what is emergentism? Well, if you've ever done any reading about emergentism, then you'll know that there are very many conceptions of emergence. And this reflects the fact that the term has been used for a long time within a variety of different disciplines, as we saw: philosophy, biology, and now physics. So here are some widely used slogans. I'm going to present an alternative and slightly more abstract way of thinking about emergence in a moment. But one conception that pops up quite a few times is unpredictability or non-derivability of certain laws from the laws governing the lower level. And certainly in the 1920s, that was the formulation that Broad chose, probably because that was a formulation that was around, that was available, and it clearly applied. Now, unpredictability or non-derivability one might see as a sign of emergence, but it's not emergence itself because, well, not in any interesting ontological sense, because really unpredictability and non-derivability are epistemological properties of a higher level science, and they may get solved when a new lower level fundamental theory comes along, or when we get better at making predictions and doing derivations. So it's hard to see them as significant in themselves, except for as a possible sign of something, some kind of deeper ontological autonomy. A different problem applies to non-aggregativity. So we often hear that emergent objects are things which are complex in that they have parts, but they are in some sense more than the sum of their parts. Once again, that's an important formulation, and it shouldn't be, as it were, sniffed at, but it doesn't always work. So some things which are widely regarded as emergent, for instance, the mind, they don't have parts, they don't have physical parts. So to say that the mind is emergent with respect to the physical, you've got a mismatch there, because the mind doesn't have physical parts unless you can say that it's already identified with something which does have physical parts, which is the brain. So you have to, as it were, apply the mind-brain identity theory before you can apply or some kind of dependence of the mind on the brain before you can apply, because it's really the brain that has the physical parts, and that's the so we use context, the term emergentist ideas in contexts in which we're not really just considering a relationship between a thing and its parts. So non-aggregativity is not always going to help. Now another idea which might be more help in the mental emergence case is the idea of there being new properties or qualitative novelty, or a kind of discontinuity in the properties between an emergent thing and the thing that it emerges from. It's, in philosophy, we call that the emergence base. The problem there is that it's very easy to trivialize these formulations. So I can take two things, two bricks, and consider them as a pair of things, and they've got a new property. Their mass is twice the mass of each of the individual bricks. So they have a new, let's suppose each brick is weighs a pound. Well, the aggregate of the two bricks has got a mass of two pounds, and that's more than the new, that's not a property that's possessed by either single brick, but no one would say that's emergent. It's kind of a boring form of new property. So we really have to say a bit more about the novelty there in order to get something going. The other type, people sometimes talk about higher levels. That's emergentists very often talk in that way, but there are different ways to get a hierarchy. You really have to identify which way you mean. So when we have a hierarchy of things, well, there are three ways I can think of. One is through parthood and composition. So you have layers, you have higher levels or layers, and each layer or level is the things at that layer or level are made out of the things at the lower level, or any lower level. So it would be an iterative or constructive conception of the layers. A different idea is simplicity and complexity. So at lower levels you'd have simpler things, and at higher levels you'd have more complex things, but then you have to find an orderly way to classify and measure the notions of simplicity and complexity. Another way possibly, as we'll see, is to use energy scales. That's a much more a way that physicists would think about it. And then finally there's downward causation. Now, in some sense, downward causation is a very helpful way, if you can get it to work, in avoiding Kim's problem of causal exclusion. Because if basically the idea is that an emergent whole is able to intervene and make the things that it's made of do something different than they would be doing if they weren't, as it were, part of that whole. That's they constrain or they push around the things in just the way that I can make my deciding to walk to the library, I can make the matter of my body go there. But the idea of downward causation is very controversial in philosophy, certainly, and in physics, and it's not always what's at issue. So it's better to explore emergence first and then see whether we can justify a claim for downward causation later. Another important contrast we have between ontological, that is concerning being or existence, and epistemological emergence. Epistemological emergence would involve, for instance, ideas like unpredictability or non-derivability or unexplainability, whereas ontological emergence is that's one distinction. Another distinction is between strong and weak emergence. That's made in many different ways, and I hesitate even to step into that minefield, but one can avoid all these choices. And following Tim O'Connor summarises his approach in a very good Stanford Encyclopedia article on emergent properties, one can be quite pluralistic about defining emergence and define it in kind of slightly more abstract terms that reflects the idea that emergence is always a sort of a middle way between complete ontological independence and on the one hand and reducibility on the other. So on this kind of more abstract view, and it's pluralistic because it's more abstract, you can fit a lot of different conceptions of emergence into it. Emergence is dependent novelty or dependent autonomy. So it involves two kinds of relation. It involves a dependence of the emergent thing on its emergent base. Here I'm using the symbols X and Y. And an autonomy with respect to them. And then the right way to think about that particular form of emergence is just determined by whatever relations you have as the dependence relation and the autonomy relation. So how far the emergence is ontological or epistemological depends on whether those are ontological or epistemological dependence and autonomy relations. So that will help you think about it. It's the details of the relations themselves which fixed what kind of emergence you're thinking about. And just to be clear, causal novelty in some sense is required if Kim's problem of causal exclusion is to be avoided. So some ability for an emergent thing to, as it were, intervene in the course of physical events. And that does mean, it does seem to mean challenging the completeness of physics. I'm now going to look at some examples of emergence. But before we do that, let's quickly review the value of emergence as an ontological framework compared to the various forms of pluralism and reductionism that we have seen in previous lectures. Well, I think that one real advantage of it is it allows us to take the ontology of particular special sciences on their own terms. So instead of taking a single ontology and saying this is how it is, you can think about, as it were, the accounts that science itself gives of how the things that it considers are constructed. They're made out of other things and the laws they're governed by. And then you can make a judgment about how autonomous and the ways in which how autonomous they are and the ways in which they're dependent. So, in other words, we can formulate a different kind of emergentist thesis, which will, as it were, track the discoveries of that within those sciences themselves. Now, John Dupre has got a nice recent discussion of the non-reducibility of biology to chemistry and physics, which he makes extensive use of emergentist ideas. He talks about the ambiguity of the notion of a gene, which is something I talked about, which is a well-known problem in the philosophy of biology. It's got a functional meaning meaning the kind of characteristic that a gene gives rise to, like the gene for blue eyes. And it's also got a separate, as it were, molecular meaning, as like a particular string of DNA. I mean, one of Dupre's claims in that paper is that molecular genes have phenotypic effects, that is, an effect on the appearance of the fully developed organism, only in a complex system which is structured and organized by previous evolution. So you have a gene for blue eyes, you've got a bit of protein, you've got a string of DNA, sorry, and that DNA is part of, that bit of DNA is part of the, as it were, developmental process that brings about the blue eyes in a particular organism. And it might have a quite different effect if you look at it in the context of a different complex system, like a different organism. It might do something else entirely, and that's typically what you find in biology. So there's no one-to-one correspondence. But the point now is that Dupre is emphasizing the as it were, the organization that a gene needs around it. A gene now considered as a molecular item, a gene needs around it in order to do anything at all in the development of an organism. Now, I've written a number of papers defending emergentist ideas about chemistry. I talked about that in the first lecture. And this emergence, I have argued, appears at two different levels. One is in the relationship between molecules and the macroscopic substances they compose, and how molecules have very complex interactions which give rise to the behavior of macroscopic substances. So there's no simple reduction, even although one has the identities holding, for instance, that water is H2O, but water isn't just any old bunch of H2O molecules. Liquid water is a very complex bunch of, and heterogeneous bunch of molecular species that occur when you bring H2O molecules together in the context of the liquid state. And that this is what gives rise to the observed properties, water's transparency, its electrical conductivity, and so on. So the second level at which I applied emergentist ideas was the non-derivability of molecular structure from quantum mechanics. Now we're thinking, after the ontological term, as emergence as an ontological claim. We've now got to think of the non-derivability of molecular structure not as being emergence in itself, because that's a merely epistemic form of emergence, but maybe it might be an interesting sign of something else. It might be evidence for molecules or molecular structure being ontologically emergent. Moving on to condensed matter physics, Clark and Lancaster's 2017 paper, that is Stuart Clark and Tom Lancaster, a pair of physicists, they discuss symmetry breaking in crystals, and picking up on some of the points that Philip Anderson made, they argue that there is a circular justification in the explanation, in the justification of the explanatory assumptions that physicists use to explain symmetry breaking in crystals. So it's the argument circular, so because instead of having a sort of a derivation, well, here's all the states of the atoms in a crystal, and here's how we explain its properties, you make an assumption about the overall state of the crystal, and then you think of each crystal, each atom, as being, as it were, affected by that, the overall state of the crystal, so it's interacting with it. And then you show that this doesn't violate any more fundamental laws. But that's not the same thing as deriving something. You're just showing the consistency with the fundamental laws. The other example from condensed matter physics I'll turn to in a moment is soft matter physics, which is an area of condensed matter physics you may not have heard of, but which Tom McLeish, who is an expert, contributed to that field, a physicist too, has commented on in his 2019 paper. So first let me explain what soft matter is. Soft matter is that kind of matter which is easily deformed by external forces. So it's squishy. And typically, it's composed of large, stable molecular structures which interact with each other just via sort of thermal, subject to thermal fluctuations, but they're so big that quantum fluctuations, which might be relevant for smaller molecules, smaller entities, but which aren't relevant for these big lumbering things. So basically, McLeish himself studies the interactions mathematically studies the interaction between systems of large sort of floppy molecules and the structures that they give rise to. McLeish argues that soft matter physics is an autonomous subdiscipline of physics that studies processes that occur at characteristic scales and levels of abstraction. So let's consider scale first. I'll have a couple of more slides on the abstraction point. We're considering energy scales first. Soft matter interactions are typically dominated by thermal transitions. That is just to do with heat. So quantum mechanical interactions are usually negligible. So this gives you tells you that a particular theory, classical statistical mechanics, is an appropriate theoretical framework for studying these things. So in other words, it's emergent in the sense that we can just screen off some kinds of interaction. They're just not relevant, and that these particular energy scales, it's thermal energy which is important. That's just thermal energy as in the energy that makes molecules move when you increase the temperature of things, put heat into them. Then there's the length scale. So McLeish says that the typical soft matter system has got some mesoscopic structure. That is, these long molecules are several nanometers. That may sound very small, but that's quite big on the atomic scale. Soft matter physics, so big floppy molecules is one possibility. Another context is polymer materials that have cross-links between the molecules, which sometimes give rigidity between to a structure, a sort of a two-dimensional structure made out of polymers. And another relevant scale is time. So things happen on relatively long lifetimes of structural rearrangement in some things like foams and glassy materials. Long lifetimes compared to the very short lifetimes according to which more fundamental processes happen at the chemical processes, for instance. Now let's move to abstraction. Now abstraction is just in the sense that McLeish means it's just a neglect of irrelevant details to concentrate on important similarities. So that's one way to think about multiple realization. In the philosophy of mind, but already seen, one can abstract between the differences between human pain and octopus pain vis-a-vis their physical realization and see the similarities between them. And in thermodynamics, we can abstract between the different ways that having a particular temperature can be realized in different kinds of physical system and see the thing that's common between them, that is the fact that they share a temperature. In soft matter, we can see, according to McLeish, you can argue that the same mesostate can be realized by chemically different realizers. So if you've got some big floppy molecules, it doesn't matter what those floppy molecules are made of. You're just studying them, as it were, independently of that chemical realization. And you see this, for instance, in molecular biology, where proteins are considered sometimes as just mechanical as ribbons in cellular mechanisms, which have got no chemical nature. You're just ignoring the chemical nature and thinking of them being sort of having mechanical properties like springiness or stretchiness in order to be able to explain cellular processes from a biochemical point of view. Another form of abstraction is universality. So once again, seeing kinds of change and being able to find the right level of abstraction to consider things in order to identify the universal laws they fall under. So general relationships between special science properties which can be independent of the details of their realization. So it doesn't matter what's going on below. So one example we saw of that would be temperature in classical thermodynamics. On this kind of view, we would think of temperature. If we think of classical thermodynamics as a theory that identifies general thermodynamical laws which apply independently of the particular ways in which the quantities it studies are realized, the temperature and the pressure and so on. Another kind of universality would be the dependence of material properties on the number, but not the chemical nature of cross-links between polymer chains. So, for instance, if you want to think one way to explain the rigidity of a material is to think about of it as a two-dimensional structure of these long molecules, but with cross-links between them. Now, it doesn't matter what the chemical nature of those cross-links is. The point is how many of those cross-links there are. That's the point which gives the proper physical explanation of the material, the properties of the material, the rigidity properties. So it's interesting that in the critique we saw from Polger and Shapiro and other materialists earlier, when they were criticizing the idea of multiple realization, they've tended to focus on things like pain avoidance and cognitive multiple realization in cognitive sciences and biology, rather than considering these cases of multiple realization and abstraction in physics, which it's much harder to see that they would avoid in the same sort of way. Well, I'm going to conclude this lecture, and indeed this series of 3 lectures, by considering a comeback that the reductionist might make in the face of all these emergentist arguments. And that is to say, well, look, fundamental physics is causally complete. So in some sense, we're just talking about theories and explanation here. And we're talking about the limitations of human scientists and their inabilities to come up with as it were, the true exact theory of fundamental physics, or their inability to write down the complicated equations. So, as we saw earlier, that's a bit of an empty position if we're just talking about reductionism in principle, and we're considering this as an intertheoretic claim. There's a claim between fundamental physical theories and higher level theories. The emergentists can just say, well, you say it's reducible in principle, but give me the evidence. Now, if one shifts back to a kind of an ontological position, then one might say, well, there might be evidence broadly from the sciences that everything in principle is reducible, in the sense that ontologically speaking, the stuff that the special sciences consider, or the things that special sciences consider, they are actually in principle, they are ontologically reducible. The question is, what's the detailed argument for that? And in philosophy, anyway, the arguments, in my view, seem fairly thin. But the philosophers who've, as it were, bothered to make a positive case include Brian McLaughlin in this 1992 paper on the British emergentists, and the philosopher of mind and science, David Papineau. Now, McLaughlin asks the question of why C.D. Broad was the last philosopher in the British emergentist tradition. And McLaughlin argues that it's because Broad wrote his magnum opus, The Mind in Its Place in Nature, in 1925, and that's just around the same time that quantum mechanics appeared. And quantum mechanics, says McLaughlin, put an end to emergentist claims about chemistry, which many emergentists had used as a way of supporting their claims about the emergence of the mental. So McLaughlin's idea is that along came quantum mechanics, and Broad had his distinction between configurational forces and resultant forces, and McLaughlin says there's no shred of evidence that these configurational forces ever existed. Now, I think that's a very previous thing to say, and I think it's it just invites the emergentists to say, well, actually, there are configurational forces all around us. Every time you see a molecule being described by a quantum mechanical equation which is not derived from more fundamental equations, that's your configurational forces right there. So it just seems that McLaughlin says there are no configurational forces. The emergentist says there are lots of configurational forces, and that's a perfectly legitimate, as it were, standoff. So it doesn't really explain why the emergentists would retreat. Papineau makes a slightly different claim, which is that completeness emerges as the best explanation of the conservation of energy. What Papineau doesn't really do is give any general detailed historical evidence that that was why scientists and philosophers began to believe in completeness, or even that they did start beginning to believe in completeness at that time, or whether they believed it in for quite different a priori reasons, which is what I would suspect. So conservation of energy was kind of irrelevant. It's also difficult to see how the conservation of energy, I mean, one gets a mild, as it were, puzzle about understanding how energy can be conserved in the particular way that Papineau talks about, if certain forms of emergentism are true, but I don't think there's any general claim that that completeness really is a very good explanation of the conservation of energy, or certainly in any sense that it's required as the only explanation of the conservation of energy. It may appear to be the best explanation of the conservation of energy if you are minded to accept reductionist explanations, but that's the kind of thing on which the reductionist and the emergentist will differ. Now, I already mentioned Barry Lower's Nobel Prize gambit, and this is something that reductionists often say. That's, woohoo, if emergentism's true, then it must be possible to claim your Nobel Prize, because if you correctly identify a phenomenon as emergent, then you just need to send your claim to the Nobel Prize Committee, and they will say, oh, well, here's a violation of fundamental physical laws, you're due a Nobel Prize in physics. But of course, that's an entirely irrelevant criticism of emergence, because one of the things, if you construct your emergentist position carefully, emergentism should never be construed as requiring the violation of more fundamental physical laws. So this is a distinction we already saw between completeness, which is where fundamental physical laws completely determine what goes on in a system, and you can have the failure of completeness, crucially, without the violation of lower level physical laws. That's just a very, very simple point that completely takes care of the Nobel Prize gambit. Now, this is now a personal view. These arguments for the completeness of physics are very weak. They're just not very convincing, and we should be very cautious about making very general metaphysical claims on such a slim, hand-waving basis. My parallel here is the history of determinism. Now, determinism has been an idea that's been formulated and defended as long as philosophy has existed, really, as long as metaphysics has existed, the idea that the future is determined. Aristotle, for instance, considered the problem of future contingents. That is, truth about the future which are in some sense fixed now. And that's a problem that can only arise within the context of deterministic thinking. But that's one thing. What changes in the early modern period is that scientists and philosophers began to believe that determinism was true on the basis of science. And the science that they believed it to be true on the basis of was Newtonian mechanics and its explanatory successes with respect to planetary motions. And this all really begins with Edmund Halley's successful prediction of the return of Halley's comet in 1705. The comet returned in 1758, and this gave a great confirmation of Newton's laws, and especially many philosophers in the French Enlightenment in the late 18th century thought that this really established determinism to be true. And you can see very explicit claims of this sort by, for instance, Pierre-Simon Laplace. But with retrospect, determinism is not true, and the evidence for it provided by Newtonian mechanics is very weak. So we think there's another claim, a very general metaphysical claim, being made on a really rather slim basis. I mean, Laplace's argument is essentially, well, Halley's comet returned, and that was an accurate prediction about a future event some 50 years later. We must conclude that everything's deterministic. I think we should be very sceptical about making these large claims on the rather slim basis of the predictive success of a particular theory with respect to a particular phenomenon. And I think we should apply that similar sort of skepticism to claims about the completeness of fundamental physics. Once we remove that constraint, Kim's problem of causal exclusion simply evaporates, and at least some of the puzzles about emergentism that scientists and philosophers of a more reductionist stripe have entertained. Well, that brings me to the end of this third lecture, and with that I thank you very much for listening.